All right. Good morning, everybody. For this week, we'll start a brand new module. So I hope you guys had a chance to at least download module number 4, which I hope is now available in Canvas. So parang pinublish ko to kay Canvas yesterday. Kindly grab a copy of module number 4, and in this module, we will actually learn another interpolatory technique or another technique in polynomial interpolation or in sort of in interpolation in general. Kasi parang na-exhaust na natin yung polynomial interpolation from last time because yung interpolation theory na especially whenever you're using basic polynomials ay medyo parang nakaano siya, parang naka-close yung theory kasi nga kapag ka meron kang n plus 1 points, wala kang masyadong pwedeng magawa. Parang destined ka lagi to find exactly one interpolatory polynomial that will pass through all of the given n plus 1 points. And that interpolatory polynomial is of degree at most n. All right? Sabi nga ng Unisolvent's theorem, isa lamang yung makukuha nating interpolatory polynomial relative to a fixed set of data points. So ibig sabihin, wala na tayong ibang pwedeng makuha, right? So, at saka kahit ano pang method yung gamitin nyo to find an interpolatory polynomial relative to the same set of abscisses, you're always guaranteed to get the same polynomial. It doesn't matter how you get there, right? Sabi ng Unisolvent's theorem. And actually, so with that said, parang nagsettle na tayo, okay, isa lang method yung titignan natin, but of course, you can see other methods on how to come up with the interpolatory polynomial. You have what we call Newton's form and other forms na merong mga advantages over each other. But I love the Lagrange form because of its simplicity. So madaling kasing tandaan yung formula ng Lagrange form, and it's easy computer implementation. So, next thing na tiningnan natin ay, sige, alam ko na yung paano kumuha or isang paraan para makuha yung unique interpolatory polynomial. Ang second question is how good is that interpolatory polynomial is with respect to really mimicking the data that we have. So, gaano kaliit yung error pag kinuha natin yung uh, pag kinumpare natin yung interpolatory polynomial to the function that is being interpolated, right? And we have said na yung error na yun ay laging equal dito. It's a value of the n plus 1 derivative of f at some number within the interpolatory interval that we don't know, right? So we don't have any any way on how to come up with the number c that should be plugged in into the n plus 1 derivative of f divided by n plus 1 factorial times omega of x. So kung gusto nating malaman gaano kaganda yung approximation sa isang value ni x, so we will get the function value at x of our interpolatory interval minus the uh, the value of the value of our interpolating polynomial at the number x minus the value or the actual value of the function at x. So ang error natin na makukuha when we compare those two things ay equal dito. So where c is a number that depends on the value of x. Tapos sinignan natin last time, paano natin mapapaliit itong quantity na to, right? And we had mentioned that there are two ways on how to minimize that error. Number one, per the suggestion of the this form, parang mas okay na baguhin natin yung n plus 1. Really, because there is an n plus 1 factorial in the denominator here. We say na, sige, parang okay na palakihin natin yung value ni n. And that makes sense because factorials always grow faster than almost any other function. So ibig sabihin, pag pinalaki natin si n, lumalaki si n plus 1, at lumalaki ng sobra yung n plus 1 factorial. So mabilis yung paglaki ng denominator per change in x. So this quantity will hopefully move down. All right? Pero yung titingnan natin today na hindi pala siya laging mag-move down. So there's always some problems with increasing the value of n. Pero let's reserve that for later. But ang ginawa natin in the last 2 weeks, tinignan natin yung isa pang paraan, which is by choosing the values of x nicely, or the values of the abscissas nicely. Because omega is simply the product of your x minus exabytes, right? I going from 1 to n plus 1. So ibig sabihin, pag pinili natin ng maayos, or pinili natin in a clever way, yung mga exabytes, yung ating mga interpolatory abscissas, we can break down the value of omega at any value of x, or kung ano man yung measure of error natin para kay function omega, para ito will be the driving force behind making this quantity smaller. Right? So hindi tayo magdidepende solely sa pagpapalaki ng value n. And we have two results there. We said that if we want to minimize the L infinity norm, or the maximum absolute value of the error, ang pipili nating exabytes ay yung Chebyshev nodes, or yung roots ng Chebyshev polynomial, or kung ang ating interpolatory interval is other than -1 to 1, then we will scale and translate the roots of the Chebyshev polynomial. Similarly, when we want to minimize the L2 norm of omega, which is sort of a minimization of a global take on the error, then ang pipili nating exabytes ay yung mga roots ng Legendre polynomials, or a scaling and translation thereof. So yun na nakita natin. Pero ngayon, sasagutin natin yung nabinbin nating tanong, bakit nga ba, or ano yung problema kapag ka lumalaki si n sa pagpapalaki kay n? Because really, what happens here is mukhang wala naman dapat masyadong pagbabago. Kasi nga, ito ay factorial. So ito ay mas mabilis lumaki. Ito, polynomial lang naman. So kapag ka meron kang power, so x to the power n, this will grow slower than n plus 1 factorial, or n factorial in general. So titingnan natin, anong problema kapag ka lumalaki na yung value ni n? And hopefully we can suggest some remedies to this problem, right? And that's what the module will talk about. So this module is intended for hindi ko pala nabago yung year, sorry. For the 10th to the 14th of October 2022. Then I expect it will have another laboratory exercise, the first half of Lab Exer 3 on the 17th, right? And here are the things that we will do, or here are the goals for the module. First is I want you to be able to describe the Runga phenomenon, its causes and implications to polynomial interpolation. Tapos, i-derive natin yung formula para dun sa solusyon, dun sa Runga phenomenon, which are basically the use of piecewise polynomial interpolants. And third, use piecewise polynomial interpolation to solve scientific problems. Okay? So, hatiin natin itong module into 2 meetings. So, sana matapos natin siya on what do you call this? Matapos natin siya on Friday. Okay? Medyo mahaba yung title, pero umpisa natin, tingnan natin ano ba yung tinatawag natin na Runga phenomenon and how it happens. And this is rooted again on a minimization, or the minimization problem for the error term. Ito yung gusto nating pababain. And we will answer why hindi laging sufficient na pataasin si n. Alright? Kasi ano ba yung mangyayari kapag pinataas natin yung value ni n? Anyone? So what's the consequence of increasing the value of n? So ang isa niyang epekto, lalaki yung denominator. Pero in another sense, ano yung implication, o ano yung maging effect ng pagpapalaki ng value ni n? Kiefer is saying magkakaroon ng oscillations. Basically, yeah, that's what I'm driving at. Pero bakit magkakaroon ng maraming oscillations? Sabi ni Jace, mag-approach ng 0. Sino yung mag-approach ng 0? Si Mitzi naman, nalaki rin yung omega. Bakit nalaki yung omega? Aha. Well, siguro yun yung sinagot ni Raylin yung tanong ko about what Mitzi suggested. Raylin said, tataas din yung degree ni omega. Yes, because dadami yung points na ginamit. Omega increases. Talaga, parang hindi naman ako sure na mag-increase talaga si omega. There would be fluctuations sa graphs, magkakaroon ng outliers, and magko-crossover ng mas marami sa line ng mas marami. Which line do you refer to, Kiefer? But I think you all are on the right track. Medyo mas mabilis nga lang kayo mag-isip kaysa sa akin, no? Because the first step, or the answer I'm looking for, which is basically just one step ahead of increasing the value of n. Yung pinaka-direct niyang implication ay, pag lumaki si n, lalaki yung degree, hindi muna ni omega, pero tama naman, lalaki yung degree ni omega, pero ang hinahanap kong sagot ay tataas yung degree ng interpolatory polynomial. Alright? Because if you're using n plus 1 points, then we can expect to have a polynomial of degree at most n. So hanggang n lamang yung pinakamalaking posibleng degree. Pero pag pinalaki natin si n, lumalaki yung degree ng polynomial. Alright? Nung interpolating polynomial natin. And I say that will not be a very good idea, as we shall see in the following examples. So sa figure 4.1, pinagawa ko to kay Mathematica. Consider natin yung absolute value function. So yung absolute value function, siya yung kulay purple dito. So it's the V-shaped graph. And then I told MATLAB, sige nga, palitan natin yung absolute value of x ng isang interpolating polynomial. But this is a little peculiar because hindi kasi nag-work for absolute value of x. At least for x's near zero yung ating theorem. What theorem was that? Do you remember kung anong theorem yung error bound? I think it was Theorem 2.3 na nagbigay sa atin ng expression na to para dun sa error. So can anyone remind me, ano yung condition dito? Actually, nalimutan ko na rin pala kung ano yung condition para mag-hold na ito yung error. Na ito yung error term. I think para mag-work itong formula na to para dun sa error, I think si f dapat ay differentiable enough, right? So if you go back to the error the error theorem, sige na, para ma-recall ko rin kasi nakalimutan ko. Let me see in theorem, in module number 2. Unless may nakakatanda sa inyo, ano nga yung requirement to sa theorem? It's Theorem 2.4. Okay, so if you look at Theorem 2.4, f together with its n plus 1 derivatives are continuous. All right, so merong implicit assumption that this will be the error term if, or actually only if f and all of its derivatives of order at most n plus 1 is continuous. Alright, so dapat continuous at differentiable si f hanggang kay n plus 1. Right? But note that in this example, yung pinapa-consider ko kay MATLAB, absolute value of x. Hindi to differentiable at x equals 0. So we don't expect the error will behave in the same manner that we expect for differentiable and smooth functions like before, right? Na yung mga covered in Theorem 2.4. Pero nevertheless, tingnan natin, ano yung nangyayari pag pinapalaki natin yung value ni n? Nagsimula ako sa absolute value of x kasi medyo simple yung itsura ng graph. Madaling i-visualize kung ano yung mangyayari. Alright? So when n is equal to 3, then this is the interpolating polynomial that we get. Okay? So medyo malayo pa yung itsura nung absolute value graph, which is the V-shaped graph we have here, versus the degree. Actually, here I used n equals 3. Let's see. Yeah, I'm thinking I need to recheck this. N equals 3. So, So this is a degree 3 interpolating 1, 2, 3. Sorry, tama. Ito dapat ay n plus 1. Ngayon ko lang napansin. So this should be n plus 1 kasi gumamit tayo ng 3 points. 1, 2, 3. So I use 3 equally spaced points from -1 to 1. So I will have a degree 2 interpolating polynomial for the absolute value of x function. And this is what I get, this parabola. And you'll see na medyo malayo pa kasi yung meron silang error na equal dito. Or actually, I'm talking about what? I'm talking about L1 error there. So in general, para lang magamit na rin natin siya, no? Ang LP norm of a function is defined to be the integral from over some interval. So in our case, it's the interval AB ng f of x or absolute value of f of x to the power p dx, tas kukunin natin yung p truth. So, ito yung p-norm or the LP norm. So, kukunin mo yung integral ng power p ng absolute value of f, then erase mo sa 1 over p. So, you already seen this formula. The L2 norm is a special case of the LP norm. And that case, p is equal to 2. Pag ginawa yung p equals 1, so magiging ano lang siya, integral ng f of x dx. So basically, that's the area between the function, the area between the curve or between the two curves. So ibig sabihin, pwede nating tingnan yung global error dito in terms of the L1 norm to be this guy. Ito yung parang sort of the total error over the entire interpolatory interval. So medyo malaki pa. So if we will follow our instinct before, okay, mukhang kailangan nating palakihin yung number of points used. Say if I use n equals 5, you'll see that there is a very drastic improvement in the interpolation process. Okay? Mas ano na ngayon, mas maganda yung fit ng ating ating approximating function to the given function, at least visually. And then if we say compute the L1 norm of the error, or actually either L1 or the L2 norm of the error, makikita nyo, mas maganda talaga to kasi pag kinulayan ko yung may error, oops, ito lang yung error nila, right? So yung area sa pagitan ng dalawang curve, ito yung L1 norm ng error, mas maliit to talaga kaysa dun sa nandun kanina, dun sa parabola, right? And this is sort of expected, or we intuitively expect this to happen because kapag ka mas marami yung points na ginamit doon sa interpolation process, magi-intersect lagi or mas madalas magi-intersect yung function f at saka yung interpolating polynomial. Kasi nga ang condition sa interpolation ay dapat daraan yung ating approximating function sa lahat ng mga points na given dun sa problem. So if I am given 5 points, so I expect the graph of the absolute value of x and my degree, My degree 4 interpolating polynomial to intersect at least 5 times, specifically at those interpolatory abscissas. Okay? So medyo okay. Pero tingnan niyo yung mangyayari kapag ang n ay equal na kay 10. Pagka si n ay equal to 10, ito na siguro yung sinasabi ni, sino ba nagbanggit kanina? Ito yung siguro yung sinasabi ni John Rensis kanina, na parang nagkakaroon ng outliers. Kasi tingnan nyo, dumaan nga yung aking interpolating polynomial sa 10 points, or actually nag-intersect yung graph ng aking function at ng interpolating polynomial in 10 points. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh, sorry. 11 points. Tama pala na yung nandito sa figure, right? So meron akong n plus 1 ko ay 11. Tumaan ako sa 11 points. Yung n pala dito ay tama. Yun na yung degree ng interpolating polynomial. So here we have a degree 10 interpolating polynomial. And as expected, the graph of our interpolating polynomial intersected with the graph of the function mimicked 11 times. Once for every abscissa. Okay? So in-expect natin na, okay, dumaan siya sa 11. So dapat, yung interpolating polynomial ko rito, mas maganda kaysa dun sa interpolating polynomial na nakuha ko using only 5 points. Kasi mas mabilis mag-intersect, mas madalas mag-intersect yung interpolating polynomial of degree 10 kaysa dun sa function at saka dun sa interpolating interval of degree 5, right? Pero i-compare natin yung errors o yung L1 norm ng error. Yung L1 norm error sa n equals 10 ay ito, right? So ito yung area nung region bounded by the two curves. So mas malaki yung diferensya between the function interpolated and an interpolating polynomial. So I guess the AIP that we got when we used 6 points is a lot better than what we obtained when we used 11 points. So parang ito yung nag-dispel no ating iniisip natin na kailangan ko lang paramihin yung points na ginamit ko para dun sa interpolation para mas mapaganda yung result. Pero ito nga, the jump from n equals 5 to n equals 10 really made a huge difference. And that difference is not what we expected. Mukhang mas mataas yung error kapag kasi ang degree ng ating AIP ay 10 compared pag 5 lamang yung degree niya. Okay. And if you further increase this, well, if n is equal to 16, medyo, I think, mas maganda na yung n equals 16 kaysa sa n equals 10. So ito sana yung in-expect natin. Pero itong sudden jump from 5 points to 10 points really dispelled yung ating plano sana na palakihin lamang yung degree. Okay? And then you might say, okay, sir, so nakita ko na, meron kang isang exemplar na hindi laging nag-work yung pagpaparami ng points. Kasi nga, compare natin yung degree 5 at saka yung degree 10 AIP. Mukhang mas maganda yung resulta mula sa degree 5 AIP, right? So, baka naman, sir, nagkataon lang kasi yung function mo ay hindi hindi differentiable. Hindi siya differentiable sa x equals 0. So yung theorem 2.4 ay hindi nag-work, at least for x's near 0. So kaya hindi natin nakokontrol yung error. Alright? So, pero binigay ko siya dito kasi mas madali siyang example. Alright? So, pero makakita tayo sa susunod na slides or susunod na illustration ng isang function na smooth na parang ganito pa rin yung behavior. Merong anomaly na hindi okay na magparami lang tayo ng number of points used. Okay? Now, if you push it to the extreme, ito yung kakalabasan yun, nasa figure 4.2. Sa figure 4.2, gumamit ako dito ng 48 o ng 49 interpolatory abscissas. So that means the choice of 49 interpolatory abscissas will force the graph of the absolute value of x and that degree 48 AIP to intersect 49 times. Pero tingnan niyo yung nangyari. Alright. So, ito yung siguro ang sinasabi kanina ng iba yung classmates na nagkakaroon ng fluctuation, sabi ni Christian kanina. Kasi makita nyo na, although dito ay maganda yung approximation, almost dikit na dikit sila, pero tingnan nyo dito, ang laki ng oscillation. Your function value will become a very small negative number, right? Tapos bigla siya magiging mataas na positive, maliit na negative, mataas na positive, and so on. Alright? Ang laki ng fluctuation ng values. And yeah, that's one cost of using a high degree polynomial. Okay? So dun sa module, naging mas ano nga ako naging mas particular ako dun sa pagde-describe ng error kasi nilista ko rin yung L infinity norm nung interpolating polynomial. So kapag ka-apat lang, 0.428 yung maximum L2 error ng norm, L2 norm ng error, baliktad. Pag si n is equal to 8, tumaas siya, so 1.045 actually. Kapag ka si n ay 16, 14 na yung L infinity norm ng error. Okay? Tapos pag 64 na, ang laki na, 10 to the 9. So nagbe-blow up na siya. So ibig sabihin lumalaki na yung maximum absolute error dun sa buong interpolatory abscissas because of these fluctuations. Okay? So bakit kaya nagkaroon ng fluctuations? Or actually while you're thinking about that, ang tawag dun sa phenomenon na yon ay yung Runga phenomenon. So this occurs when we are using high-degree polynomials. Then nagkakaroon tayo ng oscillations between very, very huge positive values for the polynomial, followed by a very steep descent to a very small negative number. So ito yung nangyaring nagkakaroon ng crazy oscillations kapag high degree polynomial yung ginagamit natin, or what I usually prefer to call the wiggling effect o yung wiggling phenomenon. Kasi kapag high degree polynomials yung ginagamit natin, yung ating nakukuhang AIP ay sort of nagwi-wiggle. Alright? So nagkakaroon siya ng ganyang behavior. So bakit kaya? Bakit may ganung property yung mga high degree polynomials? Bakit sila nagwi-wiggle? Bakit nagkakaroon ng fluctuations kapag or mataas yung chance na magkaroon ng fluctuations between function values? I mean, from very high positive values to very low negative values. Sige, excuse me guys for 30 seconds and then pag-isipan nyo. All right, and I got a couple of answers in the chat. Kiefer said, kasi kanina pa pala yung sagot ni Kiefer. Pero Trisha submitted a new answer. Sabi niya, mas maraming roots po. Yes, that's probably one reason why. Kasi nga, kapag meron kang polynomial na mataas yung degree, ang sinasabi ng fundamental theorem of algebra, kapag meron kang degree n non-zero polynomial, meron siyang at most n distinct roots. All right? Or at most n complex roots, right? So kung meron kang degree 48 polynomial, so meron kang at most 48 distinct roots. So ibig sabihin, dapat mag-crossover ka dun sa x-axis 48 number of times. 48 pa, 1, 2, actually 40, yeah, magko-crossover ka 48 number of times. So, ibig sabihin, kung mataas na yung polynomial mo, meron kang halimbawa, p of x equals a constant, say, tawagin natin a48, x to the 48, plus a47, x to the 47, all the way up to a sub 0. So, yan yung forma, ganyan yung itsura ng ating degree 48 interpolating polynomial. So, ibig sabihin, kapag meron kang degree 48 polynomial, dapat ano man yung mangyari, or actually, may chance, hindi pala kahit anong mangyari, may chance na meron kang 48 distinct roots. X to the 48 yan. So, ibig sabihin, meron kang x to the power 48 followed by lower degree terms. Posibleng ito ay maging napakalaking number. Alright? Kasi nga, it's x to the power 48. And then also on the other side, kapag si x ay negative, actually hindi pala pwede kasi si x ay laging positive. Yung x to the 48 ay laging positive. But if you have pero meron ka ditong lower degree term, no? So pwedeng yung p of x mo napakaliit na negative number. Because of the very high degree of the terms in this polynomial. So pwedeng tumaas or maging isang napakalaking positive number yung value ng polynomial at some number x, pero pwede rin itong maging napakaliit na negative number. In an instance, kasi nga x to the power 48 yung leading term, pag kinumpute natin yung derivative nito, degree 47. So ang laki ng rate of change noong polynomial p, right? So ang bilis magbago ng x's dito. Pero, so ibig sabihin, kung mabilis yung pagbabago niya, you can really go down from a very high positive number to a very low negative number in an instant. Kasi nga, ang bilis nung rate at which P changes, right? So, pwedeng nasa napakalaking positive value ka, tas babagsak ka na lang bigla sa isang napakaliit na negative number. Okay, so that means, and that should happen if you have 48 distinct roots. Ibig sabihin, 48 times ito mangyayari. So napakalaking function value, susundan ng isang napakaliit na function value, but this time on the opposite side of the x-axis, kasi nga dapat mag-cross tayo ng x-axis 48 times. So basically, yung dual combo nung phenomena na yon, yung nagkakos ng Runga Phenomenon. Kasi nga si P has a very oscillatory nature. Ang bilis ng oscillations niya. It will go down, its very nature will force it to change very rapidly. Plus, dahil sa fundamental theorem of algebra, kailangan mag-cross tayo ng x-axis 48 times. Right? So, ibig sabihin yung oscillations niya dapat mag-cross ng x-axis. So that means from very high positive number, we can go to a very low negative number in an instant, and that should happen 48 number of times kung meron tayong 48 distinct roots. So, kaya may mga function talaga na pag sila yung ginamit nating AIPs, hindi sila mag-work ng maganda. Kasi nga kapag ka mataas na yung degree, nagkakaroon ng wiggling effect or nagkakaroon na ng Runge phenomenon na tinatawag. Right? Kasi nga tama yung observations nyo kanina, lumalaki yung degree ng polynomial, ibig sabihin dumarami yung roots niya, pag dumarami yung roots niya, nagkakaroon ng wiggles or nagkakaroon ng oscillations. And that oscillations will happen somewhere in the interpolatory interval. So dito ang ginamit kong interpolatory interval ay -1 to 1. Tingnan nyo dito sa -0.5 to 0.5, okay yung interpolation, almost identical yung function f saka yung AIP niya. Pero beyond that, dito at saka dito sa -1 to -0.5 and 0.5 to 1, ang laki nung L infinity norm ng error. Which should not happen kasi nga sakop pa rin siya ng interpolatory interval. And you can see na tama naman yung ginawa ko kasi tingnan nyo to. Nagpa-pass through pa rin yung interpolating polynomial dun sa given function value or dun sa given sa given function values. Pero yun nga lang nagko-cross siya pero biglang babagsak yung value niya all the way down on the other side of the x-axis. Tapos tataas na naman siya just to satisfy that truth. Alright? Mas mataas yung degree, mas madalas ako malamang daraan ng x-axis. So dahil doon, magkakaroon ng big drop from a big positive number to a very small negative number, and that causes yung wiggling effect o yung high oscillations na nangyayari. Okay. Now, why is it called the Runge phenomenon? Well, it was first observed by Carl Runge. Nakita niya, nag-work siya dun sa function 1 over 1 plus 25x squared. So dito, hindi na kayo makakareklamo na, sir, madaya ka kasi yung example na f na ginamit mo, hindi naman sa kanya nag-work yung Theorem 2.4. Well, now, we have the function 1 over 1 plus 25x squared, which is differentiable, I think, infinitely many number of times, right? And those derivatives are all continuous. So, ibig sabihin si f ay infinitely smooth. So, dapat mag-work na yung Theorem 2.4 sa kanya. And yet, hindi pa rin na-solve ng pagpapalaki lamang ng number of ng value ni n, yung pag-improve ng AIP. Kasi kung makikita nyo, subject pa rin siya doon sa Runge phenomenon. Okay, kaya nga tinawag natin siyang Runge phenomenon because this function was later called the Runge function. Alright? Tapos ano yung maganda sa kanya? Nasa-satisfy niya yung premise ng Theorem 2.4. But let's look at the interpolatory process. So rito, gumamit ako ng degree 10 interpolating polynomial. So ang graph ni Runge function ay ito. Nasa na? I think ito yung graph niya. yung kulay blue, yan yung graph ni 1 over 1 plus 25x squared. Pag gumamit ako ng degree 10 interpolating polynomial, makukuha ko yung medyo yellowish na graph. So, ito yon, yung ganito yung kulay. And makikita nyo, na-subject na talaga siya sa Runga Phenomenon because here you see yung oscillations, right? Or baliktad. So, makikita nyo yung very high oscillations. Maganda yung interpolation dito within the or near the center of our interpolatory interval. Pero rito nagkakaroon tayo, siguro ito yung tinatawag nyo kanina na outliers. Kasi nga kulang pa yung roots na nakuha natin over this interval. So ibig sabihin kahit pataas na ng pataas yung positive values at pababa ng pababa yung negative values na nakukuha natin for the function or for the interpolatory interval, dapat dadaan pa rin tayo ng x-axis kasi nga mataas yung degree ng interpolating polynomial. So kaya ito, nagkaroon siya ng wiggling effect pa rin. And that will still happen if we use 32 or an AIP of 32 of degree 32, all right? So yun naman yung kulay, yung 32 pala yung kulay yellow, yung degree 10 siya yung kulay medyo purple. Okay, tapos blue yung ating function. Okay? So, makikita nyo rito na visually, mas maganda yung AIP na nakuha natin of degree 10 kaysa dun sa degree 32. Kasi dun sa degree 32, medyo mas malaki na yung oscillations. Okay? So, ito yung tinatawag natin na Runga Phenomenon. So, ito yung sagot dun sa tanong natin before na bakit hindi natin pwede basta-basta palakihin na lang yung value ni n. Kasi nga, magiging subject na siya sa Runga Phenomenon. So, pag lumaki yung value ni n, lumalaki yung degree ng ating polynomial. Dahil lumalaki yung degree ng polynomial, nagkakaroon ng chance na magkaroon ng napakaraming roots. Right? And then, more roots plus high degree polynomial equals high oscillations. High and fast oscillations. Kasi nga, mabilis magbago yung function value pag polynomial of high degree ka. Tapos daraan pa siya ng x-axis, that's a double whammy. Yun yung nagkakos ng oscillations of fluctuations. And essentially, that's what we call the Runge phenomenon. So that means for some functions, we need to avoid the Runge phenomenon. At wala tayong, or wala akong i-discuss na pang-check kung ang isa bang function ay nasa subject sa Runge phenomenon. So that would be for more advanced numerical analysis na. But I hope you get the idea kung bakit hindi basta-basta kaya nating or hindi natin basta-basta itinataas lamang yung value ni n para mapaganda yung AIP. Kasi nga may chance na masubject yung ating process sa tinatawag natin na Runge phenomenon. Alright? So sir, kung ganun yung problema, paano natin mapapaganda yung error, right? Do we have a remedy to go around the Runge phenomenon? Kasi nga gusto pa rin natin mag-make sense na the more points that you use, the better the interpolatory the interpolatory function that you get. Pero sabi natin, don't bother trying it for all polynomial interpolants. Kasi nga, pag lumaki yung degree, pag dumami yung number of points na pinili mo, magi-intersect mas madalas yung function f at saka yung AIP niya. Pero the high degree of the AIP will or may cause very fast and high oscillations, and that's what we call the wiggling effect o yung Runge phenomenon. So ano yung remedyo kung gusto mong mag-stick dun sa kailangan kong gumamit ng maraming points, and so on, palitan mo yung klase ng interpolatory function. Huwag interpolating polynomial yung hanapin mo. And that's what we will look at section B. Sa section B, ibang klaseng interpolation na to. So hindi na siya AIP yung makukuha natin kasi nga na-exhaust na natin yung theory ng AIP. Kasi by the unisolvents theorem, isa lang yung paraan. Or actually, isa lamang yung nakukuha natin ng AIP relative to a given set of abscissas, right? But again, if you use a lot of points in your sampling or in your approximation process, baka maging subject ka sa Runge phenomenon. So if that is your case, wag interpolating polynomial yung gamitin mo. Probably you might want to use piecewise linear interpolants. And this is basically the use of a bunch of linear functions para kunin yung para makakuha ng isang interpolatory function doon sa ating function f. Notice my change now of terminologies. Interpolating function na to. Kasi hindi na to just interpolating polynomial kasi nga hindi na polynomials yung makukuha kong pang interpolate. Okay. Actually, I'll be using piecewise linear interpolants. So sort of I'll be pasting together lines para makuha yung behavior or para ma-mimic yung behavior ni function f. And you will see later when I flash the example na nga no, nagbe-make sense ito. Na-avoid natin yung Runga phenomenon because we are eliminating the fluctuations. We are eliminating the oscillations or the wiggling due to high degree polynomial interpolants. Kasi rito, unang-una, we'll be using a bunch of linear functions. So, ang degree ng mga polynomials na nakikita natin dito ay equal lang kay 1. Alright? Yun nga lang yung pinagkaiba, hindi ito isang polynomial lamang, pero ito ay a bunch of linear functions na gagamitin ko. So, I'll get a piecewise or a conditional function. Okay? But formally, we say, or we define the piecewise linear interpolant via definition 4.1. Meron tayong function f na defined sa interval AB. Tapos I suppose I have n plus 1 nodes between A and B inclusive. So meron ako interpolatory interval mula kay A hanggang kay B. Kumuha ako ng n plus 1 sampling nodes or interpolatory abscissas dun sa interval na yon, starting with x1 equals A and x sub n plus 1 is equal to B. Again, if n is huge, all right, so kailangan we need to be wary about the Runga phenomenon. So if you don't have any idea of how f looks like, you cannot do any analysis about it. So it's safe to assume na lang na magkaka-Runga phenomenon. Para, I mean, hindi safe to assume na magkakaroon ng Runga phenomenon, pero mag-isip ng paraan para ma-avoid yung possible occurrence ng Runga phenomenon. Okay? So kung malaki yung degree ni n, or malaki yung value ni n, ibig sabihin marami kang points, try mong gumamit ng piecewise linear interpolants para ma-avoid yung Runga phenomenon. Ano ba yung tawag sa ano yung tinatawag na piecewise linear interpolant? Ito ay isa lamang conditional function relative to the partition given dun sa set of data points na ginamit natin. So we can think of it as dividing the interpolatory interval into n intervals. So nag-interpolate tayo from A to B. Tapos sinati natin to into x1, x2, x3, x4 hanggang makarating tayo kay x sub n plus 1. So the identification of n plus 1 abscissas induces, I think, n intervals doon sa ating interpolatory interval. First is the interval x1 to xn. Second is the interval x2 to x3. Next is x3 to x4, all the way up to the interval x sub n, comma x sub n plus 1. So parang nahati natin yung interval AB doon sa sub-intervals na yun. Tapos ang gagawin ko para hindi ako, para maiwasan ko na gumamit ng polynomial na mataas yung degree kasi yun na nga yung mangyayari kapag Lagrange yung ginamit natin dito or Chebyshev or Legendre, malaki yung number of points na ginamit, ibig sabihin high degree yung polynomial na makukuha ko. And since we are trying to avoid Runga phenomenon altogether, gusto natin mababa lamang yung degree ng polynomial na gagamitin natin. Right? At ano pa bang bababa sa linear functions? Ano? So yung gagawin natin. So idea is, on each of these n sub-intervals, magde-define lamang ako ng isang linear function that satisfies three properties. Okay? Tapos yung function na yon, siya yung tatawagin kong piecewise linear interpolant of f relative to the given partitioning of the interpolatory interval AB. Okay? Unang requirement, dapat si S, ini-interpolate niya si F dun sa bawat isang n plus 1 points. So that makes sense kasi nga interpolatory function pa rin yung hinahanap natin. So dapat dadaan yung aking piecewise linear interpolant S doon sa lahat ng data points. Okay, so yun yung promise kasi ng interpolation. Pero lalagyan ko siya ng isa pang condition. Gusto ko yung piecewise linear interpolant is continuous on the closed interval AB. And then not just that, gusto ko sa bawat sub-interval, si S ay isa lamang linear function. So yun yung tatlong condition para sa piecewise linear interpolant. Dapat nasasatisfy niya yung interpolatory requirement. Dapat si S ay continuous. At pangatlo, dapat sa bawat subinterval, meron ka lamang isang linear function. Okay? Now, madali siyang makuha yung sense niya graphically if we look at figure 4.4. Ginraph ko si Runga function in blue, alright? Tapos yung kulay black, siya yung piecewise linear interpolant relative to the dotted points. So ganito yung nangyari. Imagine wala mo na yung kulay black. So nandun tayo sa kulay blue. Tapos sabi ko 1, 2, 3, 4, 5, 6, 7, 8, 9. Sabi ko gagamit ako ng siyam na points, alright? Or siyam na interpolatory abscissas. So I'll get, say, equally spaced points. I start at -1, -0.75, -0.5, and so on, hanggang makarating ako sa 1. So meron ako 9 na points. Kung gagamitin ko yung Lagrange form ng AIP, I will get a degree 8 polynomial. Medyo mataas na yung degree 8, so I need to be cautious about the possibility of the Runga phenomenon happening. So ang gagawin ko ngayon, piecewise linear interpolant yung gagamitin ko. How do we get that? That's basically considering every subinterval as an interpolatory subinterval. So yung unang subinterval natin from -1 papuntang -0.75. Ang gagawin ko ay kukunin ko yung line na magpa-pass through dun sa dalawang points na yon. And this would be S sub 1. This is the first piece of our piecewise linear function. So gagawin ko to sa bawat isa dun sa mga subintervals na yun. So sa bawat subintervals, gagawa lang ako ng line that will join consecutive nodes. Ito yung unang node, ito yung pangalawang node, connect the dots. And since I'm connecting them via a straight line, yung equation nung pinang-connect ko doon sa dalawang nodes ay isang linear function. Tapos dun sa second interpolatory subinterval, -0.75 hanggang -0.5, hindi ko muna iisipin ano yung ibang points dun sa aking set of abscissas. Iko-consider ko lang ito at saka ito. Tapos ang idea, ayokong gumamit ng napakalaking ng polynomial na malaki yung degree. So ang gagawin ko, connect the dots lamang. And then this is another linear function. And this is the linear function S2. Yung kanina siya yung tatawagin kong S1. Tapos ganun yung mangyari sa lahat ng interpolatory intervals. So meron akong 9 points here. So meron akong 8 interpolatory subintervals. Sa bawat isa sa 8 na yon, magkakaroon ako ng isang linear function. Alright? Ano yung properties ng linear functions na yon? Dapat dadaan ako dun sa lahat ng data nodes, and that is guaranteed because we are simply connecting the dots. So yung pagko-connect ng dots natin, that is actually that guarantees interpolation. Kasi nga dumaraan yung kulay black na function doon sa mga data points. Tapos, nagko-connect the dots nga lang ako, so ibig sabihin nagagaranti ko yung continuity ng piecewise linear interpolant kasi nga I can draw the black graph without lifting my pen. Kasi nga ang nangyari, nagko-connect the dots lang ako ng consecutive points. So continuous yung piecewise function na na-consider natin. Kasi nga sunod-sunod lang naman sila, ano? And then the third, and that's actually is mas obvious, sa bawat isang interpolatory interval, meron tayong linear function. Okay? So ang idea ng piecewise linear interpolant, hatiin mo muna yung interpolatory interval into a bunch of subintervals determined by the nodes that you are choosing. Then what you'll do is you find the linear function passing through each of those passing through the pair of consecutive nodes. So you go to x1 and x2 muna, get the line that passes through x1 and x2, call that s1. And then go to the second interval. Get the line or the equation of the line passing through x2 and x3, and we will call that S2. And then if we collect together S1 until S sub n, all right, magkakaroon tayo ng n na linear functions that will be our, taken together, that will be our interpolating piece, actually, anong tawag ko? siya yung magiging piecewise linear interpolant natin para dun sa function na to. And I hope you see that by design, this counters the Runga phenomenon. Kasi ang problema natin, kung AIP yung ginamit ko, meron na akong siyam na points dito, so dapat degree at most 8 yung AIP. Pero the fact that I localized the interpolation, ginawa ko sa isang interpolatory interval or interpolatory subinterval. Okay? Doon lang ako nag-work. Doon sa sub-interval na lang na yon, dadalawa lamang yung abscissas. So kung meron akong dalawang abscissas, kukunin ko yung function or yung polynomial that will pass through those two abscissas. Meron akong dalawang points. So ibig sabihin, linear lamang yung polynomial na daraan dun sa dalawang points na yon. So para naging mas local yung interpolation. Instead of in one big salvo, kukunin ko yung interpolatory polynomials from -1 to 1. Ang ginawa ko lang, hinati ko muna yung -1 to 1 into several subintervals. Tapos sa bawat subinterval, magkakaroon ako ng dalawang abscissas. Kukunin ko lang yung interpolating polynomial para sa dalawang abscissas na yon. And luckily, dun sa pag gumamit ako ng dalawang interpolatory abscissas, linear lamang yung makukuha kong interpolation. Actually, that is expected from our graphical approach. Alam na natin kasi connect the dots lang naman tayo using straight line. So, ibig sabihin, linear function lang yung nakukuha natin. Okay? So, instead of an interpolating polynomial of degree 8, ang nakuha natin ay isang piecewise function consisting of 8 pieces, and each of those pieces ay isang linear function. Okay? So I hope you get the idea of the piecewise linear interpolant. On Thursday, kailan na ba? On Friday, we will formulate kung paano nga ba nakukuha yung piecewise linear interpolant. Okay? Pero announcement, on Friday, I will be attending the strategic planning workshop ng graduate school. So hindi ko kayo mamimit personally on Friday, but what I'll do is I'll post a recording nung lecture ko last year about piecewise linear interpolant at yung susunod na topic cubic cubic splines. So that will be your ano bang tawag? Watching assignment. So yun yung papanoorin nyo on Friday. Okay? And then based on that, yun yung mangyayaring lab exer on Monday. Okay? Siguro what I'll do is this. So, if you want, pwede niyo siyang panoorin ng 8:30 to 9:30 para naka-condition pa rin yung utak nyo na papasok kayo sa Friday. And then I'll be online from 8:30 to 9:30. Feeling ko kasi nasa biyahe pa kami nun. Sa LAIA kasi yung strat planning ng graduate school. So kung nasa biyahe pa kami noon at wala pang workshop, probably I can respond to your chats live. So kung may mga questions kayo about the video. But I'll post the video later today. Hanapin ko muna yung dun sa playlist ko kung nasaan yung lecture ko about deriving the formula for the piecewise linear interpolant and subsequently paano yung cubic splines. Okay? Sa cubic splines lang naman, same idea, pero sa bawat subinterval, cubic function yung kukunin natin. And then you will realize na, sir, paano yun? Dalawa lamang yung points sa isang subinterval. Paano ka nakakuha ng isang cubic polynomial? Well, ang sinasabi lang naman ng Unisolvent's theorem, unique yung polynomial of degree at most 1 na daraan dun sa dalawang points. Pero posibleng maraming cubic function daraan. Yun yung titingnan natin sa cubic splines kung bakit unlike piecewise linear interpolants na unique yung piecewise linear interpolant, sa cubic ay medyo maraming options. Maraming tinatawag na cubic splines. Okay? Kaya lang pala baka masyadong mahaba kung papatapos ko yung buong cubic splines, no? Kasi rito meron pa pala tong error term. So, yeah, kailangan ito yung simulan nating panoorin. So siguro I'll think about it kung ano yung coverage nung papanoorin yung video on Friday. I'll let you know, and yung video na yon yung magde-determine kung ano yung coverage ng next laboratory exercise natin. Okay? So, I hope that's a good plan. Don't worry, hindi ko naman masyadong pakahahabaan, ano. For those who are requesting, inantay ko lang na almost 80 to 90% ng klase ay nakapagpasa na ng LabXer 2.1 before I upload the answer key. So hopefully that will happen within the week. All right. So, and again, if you will request for late submission of LabXers, contact your lab instructors directly. Sila kasi magde-decide kung may deductions, kung tatanggapin ba nila or hindi. Hindi ko sila papakalaman dun sa decision na yun. Alright? Ako lang yung tagagawa ng exer, ano. So sila yung nag-check and sila yung magde-decide about that. Okay? So I think that's it for today. Any questions? Okay, so if there are no questions, thank you guys for joining me this morning. Kailangan ko na kayong batian ng have a nice weekend kasi nga hindi tayo mag-meet live on Friday. Panoorin nyo na lang yung recording na ibibigay ko. And but I'll try to be online habang nasa biyahe on Friday to answer questions that you might have about the video. Para parang sinasimulate pa rin natin yung live discussion, all right? So thank you guys. Have a good weekend and goodbye.
Thank you, sir.
Yes, sir.
Thank you, sir.
All right, you're welcome.
Thank you po, sir.